Real collision. One of the simplest theory of impact collision is Newton's theorem. Newton's theorem is expressed by this formula. It's a minus fraction v1 with star minus v2 with star over v1 minus v2. The epsilon is so-called coefficient of restitution. And as usual, v1, v2 are velocities of particle 1 and 2 before collision, and velocities v1 and v2 with star represent velocity of particle after collision. Coefficient of restitution can be or is in interval from 0 to 1, where if epsilon is equal 1, so it means that it corresponds with perfectly elastic collision. And if epsilon is equal to 0, so it is another extreme value, so it is perfectly plastic collision. Perfectly plastic collision. So we can continue, we can rewrite this formula into this form: v1 with star minus v2 with star is equal minus epsilon v1 minus v2. So it's another form of Newton's theorem. So maybe for memorizing, this one is better one. Once we have velocities before collision and also coefficient of restitution is known, so the only unknowns are v1, v2 after collision. But we have only one equation for two unknowns. So if we solve any task, how to solve task on collision means real collision. So first, what is applicable almost any time or any time is a law of conservation of momentum. So it's m1 by v1 plus m2 v2 is equal m1 v1 star plus m2 v2 star. And secondly, now we can't use any other law we discussed previously, because it's not either perfectly elastic or perfectly plastic collision, but it is something between. And what happens between these extremes physically happens from the point of view of physics describes quite precisely this formula, maybe this shape. Okay, so we can, as a second equation, we can write nor equation of conservation of mechanical energy, nor equation of conservation of kinetic energy, and we write Newton's theorem. So we rewrite these equations in this way. So it is V1 minus V1 star is equal M2 over M1 by V2 star minus V2. It's from first equation, and we can copy or almost copy the second equation, so we rearrange only some terms here. So it is epsilon V1, it's from here, plus V1 star is equal, and what remains here is epsilon V2 plus V2 star. We can add these equations and we can see this will be cancelled. So we continue like this. So we can put out of the brackets V1 from this summation, and on the other side there remains V2 star plus, by 1 plus M2 over M1 plus V2 epsilon minus M2 over M1. From this we can continue that V2 star by M1 plus M2 over M1 is equal 1 plus epsilon by V1 minus V2 by, in denominator is M1 and here in numerator is this. So finally we can write the result that V2 with star is big fraction, in denominator that is M1 plus M2, and there is 1 plus epsilon M1 V1 minus V2 epsilon M1 minus M2. And the only remaining unknown is V1 with star. We could calculate it in similar way, but there also the law, in quotation, law of exchanging of indexes is applicable here as well. So we can only rewrite the formula, in fact copy the formula, but we will write different indices. So there is M2 V2 minus V1 by epsilon M2 minus M1 over, and here it is all 1. So this is the result. So now we have V1 with star and V2 with star. What are velocities after collision? If we make an energy balance, and we compare the energy after collision, kinetic energy, and before collision, so you can try to calculate it, but the result is this. So it is minus M1 M2 M1 plus M2 1 minus epsilon square by V1 minus V2. So you can see that we lose energy, not as much as in case of ideally or perfectly plastic collision, where epsilon is 0. So if epsilon is 0, we lose all energy. Because there is big difference between original amount of energy and end amount of energy, or amount of energy in the end of the process. while if we had a perfectly elastic collision, epsilon would be 1. So here 1 minus 1 is 0, and 0 by anything is 0, so we lose no energy if collision is ideally or perfectly elastic.